Welcome everyone. Today we are going to discuss on retiming. We have discussed about several optimization technique to improve timing of a digital circuit in the last class, and one of the technique we have get the overview is retiming. Today we are going to discuss about retiming in more detail. Specifically, we are trying to show how to solve this retiming problem, or how to formulate the retiming problem, and how to solve it algorithmically. So both aspects we are going to discuss today. So, as you have seen in a circuit consists of several set of resistors and combinational units like gates, multiplexer, demultiplexers, and all those stuffs, right. And our objective is always try to improve either timing or area, right. And if you think about a circuit, there are two options. We can go for combinational optimizations or sequential optimizations. So, what do you mean by combinational optimizations? We suppose, you can think of there are two resistors and there are some combinational unit in between, right. So, you can visualize your circuit is like this, right. So, there are set of resistors and in between there are some combinational clouds, right. So, the set of functionality that modify the outputs, right. So, suppose this is something like this. And if we can do several kind of optimizations on the combinational circuit, which is easy, where we can try to merge to some set of gates to reduce the size, and or several kind of optimization we can do, right. But at the end of the day, if the resistors are very far and the length of this combinational circuit is very long, so whatever the optimization you are going to do, combinational optimization you are going to do on this combinational unit between two resistors, that does not be sufficient, that may not reach your target clock, right. So, what I am trying to say is, if say this combinational delay is say 200 right millisecond, and this is say only 10 say 20 millisecond. So, you can understand that this combinational is unit is smaller than this. So, whatever the optimization you are going to do, you may not, your the design may not reach the target clock. So, in that case we have to do some kind of sequential optimizations, and one of the sequential optimization is retiming. What is this? We try to move the resistors, right. So, what we can do, instead of putting this resistor here, what we can do, we can have a smaller combinational unit here, and then we put the resistor here, and then another combinational unit here, right. So, this may be say 100 and this is 100, right. So, now we can do some optimizations here in this combinational circuit. So, this is the idea that retiming is something we are going to move these resistors in the circuit, move the resistors so that we can either reduce the number of clock period, that means the combinational delay between two resistors is less, as I saw here. Earlier it was 200, and now I just move the resistor and place in little bit in between, and it become 100 millisecond now. So, this is what is retiming. So, this is a sequential optimization where we are going to move the resistor in the circuit, so that we can improve either the clock period or the number of resistors, right. So, both can be your objective, either reducing the number of resistors or reducing number of the clock period, or maybe both. So, that can be your target, right. And we have to be we have to make sure that the input output behavior is preserved. That means, the functionality of the circuit does not change because of this particular optimizations, right. So, this is what is called retiming. So, in general, we are moving the resistor in the circuit to improve the timing of the circuit or improve the number of resistors in your design. Okay. And also we have another type of retiming called peripheral retiming, which is basically in combined with conventional optimization it works. So, basically you just place all your resistors at the input or output, right. So, that you make your whole circuit is combinational, and then you apply all the combinational optimization technique on that combinational circuit, so that optimization can be better, right, because if you have a bigger circuit, the scope of optimization is high. So, we do that, and then again you move the resistors in the circuit, right. So, what I am trying to say is that, suppose you have a big circuit and there are some resistors here and there. So, what we do, we just move the resistors at the boundary, right. So, we place all the resistors here, and this become a combinational circuit, right. So, now we are going to apply this optimizations in this combinational circuit, and then after you make the modification, we again move back the resistors in the circuit in between. The benefits of is that if you have a smaller combinational circuit, the scope of optimization is less, but if you have a bigger circuit, the optimization scope or possibilities is high. So, we have done this optimizations in a bigger combinational unit, and then again you move the resistors back to the actual circuit. So, it is called peripheral retiming. So, it is actually works with the combinational optimization technique to improve the circuit performance. Okay. So, here in an example, as I mentioned that we try to move the resistors, and how we move. So, suppose I have this circuit initially, and these are the resistors, right. This is a resistors, this is a resistors, and this is that combinational unit what I am talking about, right. So, this is that combinational unit in between. Say these circles are either AND gate or some gates. Okay. So, what is happening here, you can see that the length of this maximum length here is 1, 2, 3, 4, right. So, maximum 1, 2, 3, 4, 5. So, maximum combinational length is this, right. So, this is 5. So, number of gates in a path is 5, right. And so, whatever the delay you are going to get, the summation of the delay of for this combinational unit, right. So, all AND gate or gate, all the has some delay associated with that. So, it needs some processing time, that is the combinational delay of that particular node. So, the maximum clock period will be determined by the 5 this 5 unit of gets delay, right. And what we can do here, by retiming we can move these resistors inside the circuit, right. So, what will happen here, suppose I want to remove these resistors. So, I want to remove this resistor from here, I want to move it inside, right. So, what will happen, so this will be placed. So, when you are going to move inside, it has to place all the fan outs, right. So, it will be placed here and here, okay. And then even if I want to move this resistor further, because it just reduce the delay by 1, right. So, now still we have 4, because I just move it to 1, right. So, I can move this resistor again to this. So, what I can do, I can just move these resistors inside the circuit. So, if I move this, it will, so I cannot move these resistors here, because there is no resistor here. I have a resistor here and I do not have any resistor. So, I can move only resistor to the output only when both of the fan ins have resistors. So, this cannot be moved, but this can be moved, right, because it has only one fan in to this node and this has resistors. So, I can move these resistors. So, I can move these resistors to both the output. So, this circuit will become now like this, right. Now, I can move one resistor to the output, because both the input has a resistor. So, I can move this both the resistors from here and I can place at the output. Okay. So, this is what is shown here, right. So, this is after the first step, I move this to resistor here, and then after that the circuit looks like this, right. So, now you can see the maximum delay is 2, right, so, or 3, because from this resistor to this resistor I have 3 gates. From this input to this resistor I have maximum delay is 3. So, from 5 I have reduced to 3. So, this is what retiming does, it is moving the resistors in the circuit, so that it reduces the combinational delay. But we have to keep in mind that certain rules are there, we can only move resistor from input to output only when both the fan ins have resistor, then I can move, or if I move a resistor from fan in to fan out, it has to move to all the outputs, then only the functionality will remain the same. Okay. So, this is the core concept of retiming, and you can understand that given a bigger circuit, you have lot of options, right, lot of possibilities of moving of resistors, and this circuit is not like you have this 8 or 10 gates or only 2 resistors. Your circuit may have say 10,000 20,000 resistors, million gates, and maybe more than that also, right. So, then doing these things is physically or manually is not possible. So, we have to automate this process. So, given the circuit and the delay of these nodes, combinational delay of each node, if I give to the tool, and then we have to make it automate, right, how to automatically do this retiming, so that finally I can reach from this circuit to this circuit. So, that is what we are going to discuss more detail here. So, we have understood what is retiming, and next set of discussion will be going on how to automate this process, how we can automatically does this in a digital circuit. that we are going to discuss further. Okay. So, as I mentioned, retiming rules is something like this. So, if you have registers in both the input, then only I can move it to output, and then if I move to output, it will move to both the outputs, right. So, suppose you have like this, you have a register here, then in the output I have to move both the output, right. So, that I already discussed. Similarly, I cannot move, if there are two fan outs only register here, I cannot move it to here, because the other registers, other path does not have a register. You can understand the functionality of that particular circuit will change if you have move only one register from here to here, because this path does not have any register. So, this is the retiming rule. So, if you have to move all fan in have a register, I can move them to the output to all the fan out of the register, or vice versa, right. So, this is the retiming rules. Okay. So, again we can use this register, retiming to do optimal pipelining, something like this. You can place the register at the input, and you never know where to place, because this may be a very complex circuit. You don't know what are the parallel paths and all those things, and you can utilize the retiming to do this, right. So, what we can do, I have just shown earlier, I can take this register, I can place here and here, then I can remove this register, I can move this register to the output. So, I can move here, right, and then since I have both the input have registers, so I can remove these registers and I can place them in the output, right. So, I can place them here output at the output. Now, these two for this node there are both the input have registers, so I can place them at the output, right. So, this I can do. So, I can remove these registers, this is what I have done. So, this is this first set of registers. So, I have removed this register, then I can take these registers and I can move again. So, if I move this register, I can place them here. Similarly, then I can move this register to this place, right. So, this is the final structure we will get. So, placing the register at the input and then use retiming to move them into circuit. You can understand here. So, initially the circuit has the maximum delay of 5, now we can see the maximum delay is maximum 2, right. So, this is the maximum delay path, this is the maximum delay path, and this is the maximum delay path. So, from this 3 I move from 5 I move it to 2, right. So, this is also we can done. So, pipelining in the sense we place the extra registers at the input, and then we can utilize the retiming tool to move the registers in the circuit to make to improve the pipelining. Okay, right. So, this is something we can also do. Okay. So, now we are going to talk about the automation part, how to do the retiming automatically. So, for that we have to model that circuit using a graph, right. How we can do that? So, given a circuit, so suppose I have a circuit like this. So, this is a gate, say there is a resistor here. So, I will just take a simple example. Suppose I have these resistors. So, this is a node V1, this is V2 and this is V3, and this is a resistor R1. So, there are two resistors here, right, 2 R, this is 1 R. Okay. So, what I am going to do here, I am going to construct a graph from this circuit, where I have for each gate I have a node here, right. So, I have a node for V1, this is the graph, circuit representation graph, and V3. So, I am going to have a node for each gate of your circuit, right, and this resistors will become the edge weight. Okay. So, this resistor, since I have a resistor here, this will become 1 W. Okay. That is the weight of this edge is 1. Similarly, there are two resistors here, you can I just mentioned there are two resistors between these two. So, the edge weight of this node will become 2 W. Right. So, this is what the way we are going to represent the circuit as a graph. I will repeat again. So, we will have a node for each gate. I have a node set of vertices, set of edges, and the weight, and D and W I will come to into that. So, for each gate of the circuit I have a node in the graph, and edge is basically the connections between the gates, and this resistors become the edge weight, and that is the W, right. So, for every edge there is a edge weight, and if there is no resistor in between, the weight will become 0. So, suppose I have another gate here, say V4 to this, there is no resistor here. So, V4 to, and the weight of this will become 0, right. So, I will put weight associated to each edges, right, and weight is nothing but the number of resistor present between these two gates. Okay. And also I have dV, delay of the gate, right. So, all gate has some delay associated with that, and that will has to be the input of your circuit also, and we have some usually we have a statistical data for a particular target architecture, say for FPGA, say Xilinx vertex 4 or say vertex 6 or Altera statix 5 or statix 10 or say ASIC target. So, for every cell library, for every gate we have some estimation of a delay for each gates, right, and that value will be associated with each node, right. So, we have say delay of this node, let us say 2, this has say 1, this is 5, this is 10. So, that delay dV for each node will be associated to each node, right. So, that will be given by the D, which is nothing but the delay of that particular node, combinational delay of that particular node, right. So, this is how we are going to represent a circuit using a graph, right. Just to elaborate, there is an example here. So, suppose this is my circuit, I have adder, multiplier, those in the circuit, and these reds are the 2 resistors, right. So, if I represent into the graph, I have for each edge, there is a edge here. So, I have nodes for each gates or say combinational unit, and there are 2 resistors here. So, weight will be 2, all other edge there is no resistors in this edges. So, their weight is 0, right, and we assume that delay of the combinational unit say 3 and multiplication is 7. So, this is 3, D of this node is 3, this is 3, this is 7, right. So, this is that graph represent, and so suppose this is host means say input, and so I will have a node of input and which is the combinational delay is 0, because this is just a starting point of your circuit. So, this is how we are going to represent our circuit, digital circuit using a graph. Okay. So, this is I think clear, and we since we do not have a combinational loop or say cycle in a digital design. So, we should not have any cycle in the graph which is which has weight 0. That means, you should not have any loop. For example, this is a loop, right, this is one loop, but this loop should not edge weight, total edge weight of the particular loop should not be 0. That means, there is no resistor in that loop, because combinational loop is, or the combinational cycle is not allowed in a digital circuit, then the behavior will become inconsistent. So, there is no combinational loop in the circuit. So, this is just you can assume that this is a specification or the requirement for a digital circuit. So, that should be there in the graph. Okay. So, this is how we are going to represent the circuit, okay, using a graph. Okay. Now, we are going to talk about this path. So, path is nothing but is a transition, right. So, sequence of transition. So, this is a path, or say this is a path, or from this node this may be a path, right. So, path is sequence of transition. So, this is what it is. So, V, E, V1, V2, V to Vk. So, there may be a path of this may be a path from V0 there is a edge to V1, V1 to there is a edge to V2, and so on finally to Vk, right. So, these are the edges. So, now if we take a path, we can calculate the summation of the delay of that path, right. So, this is the summation of the nodes, delay of these nodes, right. So, for example, so this is the summation of the delay of the nodes in this path. Similarly, we can find out the weight. Weight is the weight of the edges, right. So, E1 to Ek minus 1, E0 to Ek minus 1, all the weight of the edges, right. So, that will be the summation of the weight of that path. So, whenever you consider a path in a graph, we can which represent a digital circuit, we can think of the delay of that path, which is nothing but the summation of the delay of all the nodes of that path, and weights W of that path is nothing but the weight of the edges, right, which represent the number of resistors in the path, right. So, this is the two parameter we are going to define for a path, right. So, for example, if you take a path from this node to this node, what is the total weight? So, as I mentioned, addition is 3 and multiplication is 7, combinational delay, and the host node is 0. So, for this path total delay would be 13, 3 plus 3 plus 7. So, 3 plus 3 plus 7 plus 0, which is 13. So, this is dP. dP of this path is 13, because this is 3 plus 3 plus 7 plus 0, right. So, dP is 13, and Wp of this path is what? WP is 0 because there is no resistor here, there is no resistor here, there is no resistor here. So, the WP is 0 for this path. Okay. If you take another path say from this to this, what is the DP? DP is 0 plus 3 plus 3, right. So, this is 6 and WP is 2 because I have a resistor here 0 2 plus 0. So, this is 2. So, this is how we can find out the DP and WP for a given path. Okay. So, for example, the example that is given here is that this is that biggest combination. So, if a WP is 0 for a path, that means this is a combinational path, right. There is no resistor in that path. Okay. And you can see in this particular circuit the maximum length combinational path is 13 because this is the maximum possible path which is the combinational path, there is no resistor involved, right. So, this is the maximum length of a path which has WP 0. So, that means there is no resistor here. So, that is the and the delay of that particular path is 13. Okay. So, this will determine the clock period because this is the maximum possible combinational path and whatever the 13 unit, your clock period should be at least 13. So, that these operations can be executed, right. And now, the question is here, can we reduce this combinational DP of the maximum DP of that particular circuit to 7. So, that is what we are going to answer and can we do it automatically. So, that is the two component here. So, we have understood this for this particular graph or this circuit, the maximum length of the delay of a combinational path is 13 and can we make it 7 by retiming or moving the resistors. That is something we are going to discuss, or can we how we can do these things automatically, that we are going to discuss. Okay. So, so this is something the problem statement for now and we will take this example throughout this discussion to see how whole things works, the retiming automation part. So, before moving to that the automation part of the retiming, we will talk about the how to solve set of inequalities. Okay. How we can solve that particular set of inequalities, that we will discuss because that we will be going to use in later. Okay. So, the inequalities, if your inequality is in the form of this, right, so, that it is always like this R 1 minus R 2 less than equal to 0, R 3 minus R 1 less than equal to 5. If you have this form where k is an integer, so all are integers, and say suppose we have set of inequalities is m, okay, 1, 2, 3, 4, 5. So, I have m equal to 5 here and number of variables here R 1, R 2, R 3 and R 4. So, n equal to 4. So, if you have given a set of such inequalities, right, and you have to find out the value of this R 1, R 2, R 3 and R 4, which satisfy all these constants, right. So, this is your problem statement, that if you have given a set of inequalities over n variables, m inequalities over m variable, and we have to find out this value of the variables which satisfy all these constants. So, that is how we can solve that problem, and we will discuss how this particular problem can be mapped to shortest path finding of graph, right. We try to map this particular problem to shortest path problem of graph, and we can solve this particular problem using finding all pair shortest path in a graph or or single source shortest path algorithm to solve these inequalities. So, that is something we are going to discuss, right. So, we understood that we have set of inequalities, number of variable is n and we have to solve these inequalities, that means we have to find out the value of the variables which satisfy all these registers, all this constant. Okay. So, for that what we are going to do, we construct a graph out of it. Okay. What we can do, for each variable I will consider a node. Okay. So, I have four variables here. So, I am going to consider R 1, R 2, R 3 and R 4. I will consider a node for each variables, and I will consider an additional node R extra, what if there are n plus 1. So, this is 5 for me. So, this is an additional constant. Then what I am going to do? I am going to add edges here. So, from this extra node I am going to add a edge to all the node of weight 0. Okay. What I am going to do? This is all weight 0. Okay. And for each inequalities like this, from Rj to R 1, so say R2 to R1, I am going to add a edge from R2 to R1, from this to this. Okay. So, R2 to R1 with weight this. Okay. So, for example, this 3 to 1 to 3, 1 to 3, I am going to add a edge of 5, then this is 1 to 4, 1 to 4, I am going to add a edge of weight 4, from 3 to 4, 3 to 4, I am going to add a edge of minus 1, and from this 2 to 3, 2 to 3, I am going to add a edge of 2. So, this is that graph representations, and now we can show that if we the value of R1, R2, this R2, R3 and R4 is nothing but the shortest path from this node to that particular node. Okay. So, if you just see here, so the shortest path from this node is 0, right, because so there are many paths. From here I can go through this, or I can go through this, or I can go through some other path also. I have two paths. For example, for this node I have one path through this, I have one path through this, right, or I have one path through this also. So, for this path weight is 2, 0 plus 2, 2, for this path weight is 0, and for this path 0 plus 0 plus 5, 5. So, shortest path is 0. So, there are 3 possible paths, and the shortest path is 0, right. So, we can show that if we construct a graph like this from this inequalities, that the shortest path from this node is nothing but the solution of this, right. And intuitively what is the fact? So, suppose I will just take a example R1 minus R2 less than equal to minus 2. Okay. So, so in this cases I have only this constant, right. So, this is R1 and I have to find the value of R1 and R2 which satisfy this constant, right. So, I have R3 extra node and this is 0, this is 0 and this is R2 to R1 is minus 2. So, now think for this node I have only one path. So, R2 is 0, shortest path is 0 because this is 0, and for this node I have two paths. So, this distance is 0 and this distance is minus 2. So, the minimum path is this, right, this one. So, R1 is minus 2. So, you can see here that R1 less than equal to R2 minus 2. So, whatever the value of R2, R1 should be less, at least 2 less of that. So, this is satisfying this, right. We can have many value solution. It can be say this will satisfy say R2 equal to say 5 and R1 equal to 3, that is also satisfy this constant, but we need one solution that is satisfying this condition, right. So, so you can understand the shortest path actually give you. So, if this is 2 shortest path you can find out from this extra node to this particular node, that will give you the solution of this, at least one solution, because we can have multiple solutions, but we need one solution to this of this list of inequalities, right. So, this is how we are going to solve this set of inequalities. So, what we can do? We are going to construct a graph as I am a constant graph from that. So, as I show here from this set of constant graph, this is my constant graph which I have already drawn. So, I have set of nodes for this each variable, and we have a extra node V1. From this I have a all for to all this node where 0 node is there, and whenever there is a edge from constant like Ri to Rj, I am going to add a edge from j to I, okay, with weight k. Okay, this is what I have done and discussed, and then the solution of this particular inequality is nothing but the shortest path from this node to all the node. So, if you solve this path, we can see that R1 is 0, this is R1. R1 is 0 because I have two paths here. I just showed one path here, both are 0. So, R1 is 0. For R2 this is also 0 because there is only one path possible. So, R2 is 0. For R3 I have seen there are two paths, but this is minimum. So, R3 also 0, and for R4 I have this path weight is 0 and this path weight is minus 1 and this path weight is 4. So, this is the minimum one. So, R4 is minus 1 and R5 is 0, which does not matter to us. So, this is the solution, and we can see that if you just put this value to here, it will satisfy all the constant, right. So, this is how we are going to solve a set of inequalities, okay, of the form of this. So, this is what I have shown here. So, we can use Bellman-Ford algorithm, single source shortest path problem, which given a graph we try to we will consider this is the source and we try to find the shortest path. So, how the Bellman-Ford algorithm works? So, it works iteratively. So, in first iteration it try to find out the shortest path from this node to some node of length 1, then length 2 and length 4, length 3 and so on, finally length of n. So, it will need n number of iterations. So, finally, I am going to after n iterations, because I have n variable here, I will get the shortest path. Okay. So, if I just do this, so I will so this R 4 1, so this will give you 0. So, the same solution I am going to get. Okay. So, I am not going to disturb this Bellman-Ford algorithm, which we can learn from other sources. Similarly, we can apply Floyd-Warshall algorithm. So, this is all pair shortest path. It actually calculate using some matrix. So, this R 0 R 1. So, if this is R 0, that means all shortest path from node V I to V j through node R 0 or V 0, and then this R 1 means all shortest path using V 0 and V 1. So, if I go for say 5 iterations, so using all the nodes, right. So, since I have 5 nodes here, if I go for 6 iterations, it will consider all the nodes from 0 to 5. So, all this R 0 to R 5 will come into picture, and then this is something. So, this is R 5, right, this is R 1, this is R 1, this is R 2, this is R 3, this is R 4. Similarly, this is R 1, R 2, R 3, R 4 and this is R 5. So, R 5 is my that source node, right. So, from that node, so the last row will give you the solution. So, R 5 to R 1, this is the shortest path length. From R 5 to R 2, this is the shortest path length. From R 5 to R 3, this is the shortest path length, and from R 5 to R 4, this is the shortest path length, and R 5 I do not care. So, this is the solution which we have also saw in the last algorithm. So, once we construct this constant graph from the inequalities, either we can apply Bellman-Ford algorithm or Floyd-Warshall algorithm to find out the shortest path. Okay. But provided there should not be any negative cycle, and this Bellman-Ford algorithm can actually detect that. If you have a cycle, negative weight cycle, so for example, suppose I have a cycle like this. So, this is -1, this is -2, this cycle is -3, right. If you have a negative cycle, so there is no shortest path. So, if you rotate one time, this is -3, 2 times, then -6, -9 and so on. So, we cannot find a shortest path if you have a negative cycle. So, using Bellman-Ford algorithm also we can find out whether there is a negative weight cycle in the graph or not. If there is no, then we can solve the problems. Okay. So, this is how we can solve the inequalities, and we are going to use this particular thing in retiming. We will come into discussion on that. Okay. So, now we will talk about how to automate this retiming process. Okay. So, you can see that retiming, what is happening, we are moving the registers, right, and how we can define that, how many registers are moved. So, for that what we are going to do, suppose I have a edge like this and say the W is the weight here. So, this is my edge E, this is the node U, this is the node V, and so initially the number of registers is W. So, how many registers will be there after the retiming? If some registers move from here, so it is depends on the number of registers move from this side to this side, and number of registers move from this side to this side. Okay. So, let us say the number of registers move from this to this is R V, okay, and the number of registers move from this side to this side from the output to input of the node U is R U. Okay. So, this R is for a node is given by this value is like if the number of registers move from the output side to input side of that node V, right. So, R V means number of registers move from the output side to input side of the R V. So, that the final value of this register W R after retiming, what will happen, W plus R V, because that is come in and that is going out, right, R U. So, the after retiming, the number of registers in this particular edge will be given by W E, that is this weight of the edge, actual weight, then the R V minus R U, right. So, number of registers come in, number of registers go out plus the original registers. So, that will give you the number of registers after retiming. Okay. So, what it indicates, if we can find out this R value for each node, then we can calculate the retiming value, right, because we are now going to talk about the automation, how we can do that. So, what we are going to talk about, we are going to consider a variable R V for each node V of the registers, which define the number of registers that is moved from output side to input side of that particular node. Okay. And if we know the value of that all this R value, the R value of all nodes, then I can recalculate the recalculate the edge weight after retiming. So that that will define your retiming, right. So, this is something what I discuss here. So, retiming is something solving this problem, how to find out this R value for each node, right. So, what we are going to do that, we are associated a level, vertex level for each node R, and which will define the number of register that is moved from the outside side to input side. Okay. So, that is RV. So, you have, so if you have number of nodes in n, so how many variables are you have? N number of variable R1, R2, R3 to Rn, right. So, those number of variables are there, and if I know the value of all these variable, we can find out the number of register in each edge after retiming. Okay. So, conceptually this is shown here. So, if there are two registers at the input, and if you move to this register at the output, right. So, that means the number of register moved from this side to this is -1. So, retime by -1, right, because you are moving the register from input side to output side. So, the number of register moved from output side to input side is -1. Similarly, if you have a register at the output and you move them to input, that means the number of register moved from here is 1. So, retime by 1, right. So, this is how we define the R value. So, for this node R value is, if you have moved, if this happens, so this RV value will become -1. If this happens from this to this, then the RV value will become this is -1, this is 1, because that is what is discussed, that is given the number of register that is moved from the input side to output side. Okay. So, this is something. So, if you have this, if you know that RV equal to -1, then I know there are set of register from input side moved to output. If the RV value is 1, that means I know that the one register from the output is moved to the input, right. So, this is what is given by this. Okay. So, for this case, this is RV equal to -1, because number of register moved from input to output is 1. Okay. So, this is how we can determine the weight of the edges after retiming. Okay. And we are going to find out these values, R values. So, our objective is to find out the R value, the level value, the register value, this R value of each node, which with which we can actually identify the retimed circuit. Okay. So, here again one example for that to clarify your things. So, suppose this is my U node and this is V node, and say RU equal to -1 and RV equal to also -1. What does it mean? So, if it is -1 means what? Number of register move. So, this R means number of register move from output to inputs. This is -1 means effectively one register move from the input side to output. So, what is happening? So, one register move from to this. So, this will become 1 and this will become 1, this will become 1, because that is what given by this RU -1, right. And then again this RV also says the number of register move from output to input is -1, which is means number of register move from the input side to output side is 1. So, this is moved to this. So, this becomes 0 and this becomes 1. So, this is the retimed circuit. So, if I know the value of RU and RV, I can find out that I actually move this one register from here to this place and this place. This is what is given by this value, right. So, this is what, if I know this value of RU and RV is this, and say this is 0, other are 0. So, this node is also 0, this node is also 0, then I know that after retiming the circuit is like this. So, what is mean basically? There are two registers initially here, I move one of the register to these two places, okay, and I keep one register at the original place. So, this is what is retiming does, right, and you can see here the maximum delay will become now 6, right. So, for this node this is 6 and this is also 7. So, the maximum delay will become 7. So, I understand that. Okay. So, this is how we can will do. So, we consider a variable R for each register, and we try to find out some set of inequalities now or constant which will satisfy by this R, okay, that we are going to discuss. And then we try to solve those particular set of inequalities using that shortest path problem, which will give you the value. Okay. This is the overall approach. So, what is the set of constant now? The first constant is that if you have a path here, weight of that path after retiming cannot be negative, right. You cannot have a negative weight, because your register cannot be negative, maximum it can be 0, it cannot be -1 or -2, right. So, the first thing is that if a retiming is legal, that means your this WR is given by the weight of the register after retiming. So, W is the weight of the register before retiming, and WR of edge E is given is represent the value of weight of that particular edge after retiming, right. So, what does it say? That WR, so this is the edge E. So, WR of E should be 0, should be greater than 0, because your weight should not be less than 0. So, this is what is the first constant. Okay. So, for every edge, weight should not become negative after retiming, because if you put say, so suppose this W of the edge is say 0, okay, and you, so this is say U to V, okay, and suppose you give the R V is 1 and R U is 2, okay. So, then what is happening? So, you are saying that number of register come here is 1 and number of register goes from this register is 2. So, finally, the final value of this register is given by this. I know that I already discussed the W plus R V minus R U. So, that is W R is nothing but W of E R V minus R U, right. So, now this will become W is 0, I consider is 0, this is 1 and this is minus 2, this become minus 1. That means, you are assuming that after retiming this edge has minus 1 number of register, which is not feasible. So, if you solve this inequalities using this, which is wrong, right. So, this is not a valid solution. So, we should have some constraint on this variable, because any kind of value is not a solution, right, because some of the solution is not illegal, some of the solution is not correct or illegal for a digital circuit. So, we have to add set of constant which is called feasibility constant. Okay. We will consider called the feasibility constant, that number of register for each edge cannot be negative, right. So, it should be after retiming, it should be greater than 0, which is W R greater than equal to 0, which is nothing but W E plus R V minus R U greater than 0. So, if you just rewrite this, it will become form like this, R U minus, you just rewrite this, I mean put this W this side and you just do this. So, you will get this equation. Okay. R U minus R V greater than less than equal to W E. So, this is for each edge, which is called feasibility constant. So, you should not have any kind of value of the R, so that your edge weight become not negative. Is not, so that we are restricting this value to this variable, so that we cannot have a solution which result in this. Okay. So, if you have a set of inequalities like this, which ensures that whatever the solution you are going to get is it does not result in some edge which has negative weight, right. So, that will be restricted by this constant. Okay. So, next is called critical path constant, that I am going to come after we will discuss. Okay. So, before that we are going to discuss two important parameters, this W and D. Okay. This is used in the second constant. So, let us discuss that. What is that? So, if you just consider a path from the node U to V. Okay. So, you can have multiple paths here, right. You can have multiple paths, okay, and say there are 4 paths here, okay, and say that the weight of this node is say 4, this is 4, this is 3 and this is 3, okay, or say this is 5. The number of registers, weight means number of registers in this path. So, so from a node to another node, there may be multiple paths, not just one path, right. So, I assume that from this node to this node there are 4 paths, and the number of weight here is 5, weight is 4 where, weight is 3 here, weight is 3 here. Okay. And now, so that is given by the WP. Okay. So, this is something WUV means the for all path from U to V, which has the minimum weight. So, for example, here, so for this particular example, W U to V will be 3, because I have 4 paths and I assume the number of register is 5, number of register is 4 here, number of register is 3 here, number of register is 3 here. So, there are 2 paths which has number of register is 3. So, W U to V is 3. Okay. So, W U V. So, for each pair of U V, I can find out this value. Okay. Similarly, that DV says what? So, for all the paths from this U to V, for all paths from U to V, if the weight is minimum among the paths what is the maximum delay. Okay. So, suppose that d of this node is say 12, this is say 10, this is say 15, and so this is say 5. So, although so this is say this is 50. Okay. So, although this particular path, so there are 4 paths and the minimum delay maximum suppose this value I consider as 8. Okay. So, I am going to consider out the maximum delay which is basically this 15, right, but I am going to consider only the path which has minimum number of registers. Okay. So, I am going to consider all the path which has minimum number of. So, although there are 4 paths, I am going to consider only these 2 paths because these 2 paths have a minimum number of registers, and then I am going to consider the path which has maximum delay value which is 15. So, du to v will be 15 for this. Okay. So, this is the 2 parameters. So, this is a matrix, right. For each pair of u and v we have to calculate this, okay, that maximum minimum number of register between any 2 nodes, and among the paths where we have minimum number of register what is the maximum delay. So, these 2 value. So, example I have taken here w will be 3 and delay u will be 15. Okay. This is how these 2 parameters says. Okay. So, if you just take our same example, that example we have considered so far. So, you can see that the maximum. So, if you just consider so v, so this is the matrix, it will be given by a matrix because any pair of paths from any v to v. Okay. So, so all this v 0 0, v 1 1, v 2 2 will be 0 because this is the number of register between 2 node is 0. So, this all this will be 0. Okay. So, this is given by the w parameter, and if you consider any 2 pair v 0 to say v 3, how many paths are there? This is one path, this is one path, and this is another path. There are only 2 paths. So, this path has 2 register, this path also have 2 register because there are 2. So, this is 2. Okay. So, v 0 to v 2, v 3 is 2, v 0 to v 1 also there is one path, weight is 2. So, this is 2. So, v 0 to v 3 also there are v 0 to v 2 there is one path and weight is 2. So, all are 2. So, now from v 1 to v 3 there are 2 paths, both are 0. So, this is 0. v 1 to v 3 there is one path, weight is 0. So, this is 0. So, this is how we can represent this w, which is giving the minimum number of weight between any 2 pair. So, for example, say v 3 to v 0 there is only one path, weight is 0. Right. So, v 3 to v 1, v 3 to v 1 I have one path and the weight is 2. So, this is 2. So, this way we can actually construct this matrix where any pair vi to vj that will give you the minimum number of register possible in all path among these 2 nodes, minimum number of registers in that all the paths where we have the number of registers minimum. Okay. So, this will be given by this w. Okay. Similarly, now we are going to consider all the path where the weight is given by w u v, what is the maximum delay that is given by this, right. So, if you just take again that example, this example. So, for example, say again this v 0 to say v 2, okay, let us calculate. So, this is weight is 0, this is 3 and this is 3. So, I have 6. So, and I have only one path, right. So, v 0 to v 2, v 0 to v 2 6, v 0 to v 3 how much? There are 2 paths, this is the path, this is the both the path has minimum is 2. So, and this path has 3 plus 7 is 10, this path 3 plus 3, this path 3 plus 3 plus 7 which is 13. So, I am going to consider the maximum because both the path weight is 2. So, this is 13 and you so similarly, so you just take say v 2 to v 1, okay, v 2 to v 1. So, this is your v 2, the path is this, right, this is the path and this is 3, this is 7, this is 0 and this is 3. So, 3 plus 7 10 plus 13. So, this is 13. So, this is how we can calculate the d. So, this is suppose these 2 matrix you have to calculate for this, which is represent the minimum number of register between any 2 nodes and among them what is the maximum delay. Okay. So, this is what we got here. Okay. So, this is that 2 matrix, and now you can see the nodes with red. So, we for this example as you mentioned earlier that maximum combinational path is 13, you can see the maximum delay of the combinational path is 13, which you have seen earlier also, and our target is to reach 7, right. Can we reach 7 for this? So, that is what we have discussed earlier also, that our target is to get 7 here, and all the nodes that are read here, that is those are the combinational path which actually do not satisfy, they have the delay more than 7, right. So, for those kind of, so they are actually critical path, right, because our target clock period is 7 and we are getting here is 13, 10, those values, right. So, those are the critical path, because they are not satisfying our target clock period. And for all such path where WP is so all this path where this dp, the delay of that p is greater than the target clock period, which is say 7 in our case, say this is alpha, then those paths should have at least one register after the retiming. Okay. Otherwise, it will not break the critical path, right. So, we have to consider all the paths. So, there are 1, 2, 3, 4, 5, 6, 7, 8. There are 8 paths here. Those paths are actually failing, fail to satisfy the critical target clock period, which is 7 in our case, and we need at least one register on those paths to break the critical path. So, this is given by the critical path constraint. So, for all the paths where the dp, the delay of that path is greater than the target clock period, on that path the wp should be at least greater than, right. So, this is what is given by the critical path constraint. So, this is what is given by this. So, how we will get this we will discuss. So, after the, if you just think about say path here, which is very important. So, I just consider a path here from u to v, and you may have some v 1, some other node also, right. So, this is that node path where WUV is minimum. So, this is the path, there are minimum many paths. Now, I consider a path where this is minimum, WUV is minimum and dp is maximum. So, this is given by one path. So, this is that path. Okay. So, now in this path what is happening? So, I know every node associated with a R, right. So, this is RU associated here, this is RV1, RV2 here, RV3 here and so on, right, RV4, sorry RV, right. So, what we are going to consider is that is the final value of this RV. So, if I know this means the number of register move here from this to this, right. So, here this means number of register move from the output to input here, this RV2 means number of register move from output to input here, right, and so on. So, in this case, so what is the final value of this WRP, right. So, WP is given before the retiming and WRP is given the value which is basically nothing but after the retiming. So, if we calculate that, so it is basically the WR of each of these edges, right. So, WR of every edges after retiming, which is given by WREI, right. And now, this I can represent by this, we already know that this for WR is nothing but WRI edge weight before retiming, and this RV my I plus 1 to RV my because the edge E from VI to VI plus 1. Okay. So, this is the difference between this. So, if you just calculate this, you can see that I can actually cancel out all the intermediate terms and only this R Vk and V0 comes. So, that means V0 is U and Vk is V. So, finally, the RV value of intermediate node does not matter to us, only the RV value of this U and V matter to me, right. So, WP plus RV and R minus RU, right. So, this is RV and this is RU. So, what is the important factor here is that after retiming, I should only bother about this RU value and RV value, and this will be given by, and the WP, the weight, the minimum weight will be given by WP, whatever the weight was earlier, plus RV minus RU, intermediate thing will be cancelled out each other. Okay. So, now this value should be at least greater than equal to 1, right. So, this value should be greater than equal to 1. Okay. So, what we have seen that is for a path which has minimum weight W and dV is WV and maximum weight is dV, there we can see that the intermediate R value does not important, only important factor is the start node and the end node, right. So, the final value of WRP will be given by, this is actually W, this actual WUV plus the number of nodes come into here and number of register goes from here, right. So, this RV minus 1, and what I am saying that since this is if your DV, that DUV is greater than target clock period, what will happen, we need at least one register here to meet the critical path, right. So, we have to see that this value should be greater than or equal to 1, okay. And if we just move these values, reshuffle these values, you will get this, right. So, this is what is called critical path constant. So, I have two set of constant. First set of constant says that feasibility, that means after retiming your edge weight should not be non-negative, that means you should have at least 0 register between any two gates, and critical path constant ensures that for all path where delay actually exceeds the target clock period, which is say alpha, where dp of that particular path is greater than alpha, I ensure that those path, all possible path have at least one register, so that you meet the critical path. So, if you have these two set of register, set of constant, and then we try to solve this. So, we will get set of inequalities now, right. So, these are all basically represented by the inequalities of the form we have discussed earlier, right. So, here if we take the same example again. So, for each edge I have this feasibility constant, okay. So, from V0 to V1 the form is like this. So, RU minus RV less than or equal to WV. So, I will have this R0, RV0 minus RV1 should be less than or equal to 2. So, I have 1, 2, 3, 4, 5 edges. So, I have 5 constant like this, okay, 1, 2, 3, 4, 5. So, for example, RV3, so edge from V3 to V0, V3 to V0, I have RV3 minus RV1, V0 should be less than or equal, so it will be 0. You remember that I have assigned RV0 here and RV3 here, RV2 here and RV1 here, and our objective is to find the value of this RV0, V1, V2 and V3, right. And I am adding constant. The first set of constant is called legal constant or the feasibility constant, and for each edge I have to add this, right. So, I have 5 edges, I have added 5 constant like this, and now I have to consider all the path where delay is greater than target clock period, because our target clock period is 7 in this example. So, I have all these scenarios 3, 4, 5, 6, 7 and 8, those are the path which delay is more than 7, because they are more than 7. For those path I have to add a constant, right. So, if I just consider say this value, this is V1 to V0. So, V1 to V0 I have to add a constant like this RU minus RV less than or equal to WUV minus 1, right. So, the WUV value will get by this parameter, right. So, if you just consider say RU minus RV. So, if you just consider this, say this value, okay. So, this is V3 minus V1, V3 minus V1 should be V3 minus V1. So, this is V3 minus V1, that means RV3 minus V1 should be WUV, WUV of V3 V1 is 2 minus 1. So, this will become 1, right, 2 minus 1. So, similarly, if I take another value, say this one, this is V1 to V0. So, V1 to V0, this is V1 to V0, and for this node RV1 minus R0 should be WUV is 0 here. So, 0 minus 1. So, this is minus 1. So, this is how this constant added. So, for all this value I am going to add a constant like this, okay. So, I have now set of inequalities. So, this is feasibility constant and this is critical path constant. So, now I am going to solve this constant. If you solve this constant, I will get the value of RV0, RV1, V2, V3, right. So, this is and for that I already discussed how to solve the set of inequalities using a shortest path problem. So, what we are going to do, I construct a constant graph as I discussed earlier from all this constant. I will get this kind of constant graph, and then I apply the shortest path algorithm like single source shortest path Belmont-Ford algorithm or Floyd-Rowley algorithm to get the values, right. So, that will give you the shortest path value from this extra node. So, constant graph, there should be another node here which is, so from where this 0 should be added. So, this is 0 0 0 and then this is R5. So, this R5 to this node will give you the minimum value, right, and solution to this problem is this. So, I am not going to detail how to solve this. So, I got the value that R V 0 is R V 0, R V 3 is 0, R V 0 is 0, so this is this is V 0, right. So, this is V 0, this is 0, R V 0 is 0, then R V 3 is 0, this is also 0, R V 1 is and R V 2 is minus 1. So, this is minus 1, this is minus 1. So, this is the value we got, right, and with this value we can actually recalculate the position of the resistor, right. So, this is my initial position and this is minus 1, right. So, this is minus 1. What is happening here? So, that means one resistor is moved from this means number of resistors move from this is minus 1, that means one resistor is moved from this, right. So, one will move from here. So, this will come here and here, okay, and then this is also minus 1, this is also minus 1, means one resistor move from output to input. So, this will move from this to this. So, this will come here and this will be removed. So, you can see that for all other is 0. So, this is the final position of the resistors, and you can see the maximum delay of the critical path. This is I know this is if you remember, this is my if I remember correctly, this is multiplier and this is adder and this is adder, right. So, this is 3, this is 3 and this is 7, right. So, the delay of this path is 3 plus 3 6, delay of this path is 7. Similarly, delay of this path is so there is a resistor, this is 3 and delay of this path is also 7. So, the maximum delay of this is 7 and earlier it was 13. So, you can see that using this retiming algorithm I actually solved this problem, right. I find out the value of this variable such that this R 0, R V 0, R V 1 and R 2 such that I actually reach the circuit which is my target, and I can reach the clock of clock period 7, right. So, you understand the overall flow. So, what we are going to solve here? We try to find out the position of the resistors automatically. What we have done for that, I put a value variable, I consider variable for each node which define the number of resistor moved from the output to input, and we try to find out set of inequalities, one set of inequalities for the feasibility, one set of inequalities for the critical path, and we solve those inequalities using shortest path problem, shortest path algorithm like Bellman-Ford or Floyd-Warshall algorithm, and that will give you the value of those variables, the R value, and using the R value I can recalculate the resistor weight for each edge, and so that which actually give you the retimed circuit. So, I can see that from this from this circuit where I have two resistors here, I actually using the retiming algorithm I move one of the resistor to these places, and through which I can achieve the target clock period of 7. Okay. So, this is something is called retiming for clock period optimization, because I try to optimize the clock period. Similarly, we can do retiming to minimize the number of resistors also, because suppose if we just consider one example, suppose I have a example of this, suppose I have say I have 4 output resistor, right. So, if I have a resistor here and if I do a so suppose it is in other way, just a minute, yeah. So, I have say I have resistor here, right. So, number of resistor is 4, right, and if I do a retiming, I just move this resistor to the input, what will happen? I have only one resistor, right. So, the number of resistor reduce. So, this is the objective. If you have number of resistors at the fan out, and if you just move them in the fan in, then the number of resistor may reduce, or if it may be other way also. Suppose there are 2 input and 1 output. So, initially there are 2 resistors here, and I can move the resistor at the output also, right. So, then the number of resistor will become 1. So, this is the objective. If you our objective is to move the resistor in the circuit, so the number of resistor become 0. So, you remember here the latency remains same, because that whatever the input is coming, it will take 1 clock period to when 1 clock to reach the output, because one set of latency are there. Here also latency is 1, but the number of resistor is less. So, latency does not change for the circuit, but the number of resistor has changed. Okay. So, for this, so our objective of this kind of retiming is minimizing the number of resistors. So, what will be the objective? So, suppose this is the total number of resistor, I want to minimize this number. So, what will be the given value? So, the WR is the modified edge weight, right. So, for each weight this is a summation of, so that will give you the number of resistors after retiming. Suppose you do the retiming in the same way and you get this value, and which is nothing but WE plus RV minus RU, right. So, we have already seen that. So, this WE is already fixed. So, this is the summation of the WE plus the summation of the RV minus RU. Okay. So, now so this is already n. So, suppose this is a fixed number, you cannot change, this is the actual number of resistors in the circuit. So, this is n. Okay. You cannot change that because in your initial circuit has this number of resistors. And now what we can do, so now this RV and RV is associated with each node. Okay. So, now you can think of this is basically, now you can think of any node, and where I can say that what is the number of change will happen, this number RV into this. So, if this RV is for a node RU, right. So, this is a V node, the fan in. So, if you have, as I discuss here, if difference between the fan in minus fan out, right. So, here the fan in is 1 and the number of fan out is 4. So, if I move a resistor from this to this side, it will reduce, right. So, this is fan out minus fan in, the number of resistors will reduce 3, 4 to 1, right. So, similarly here, if I move a resistor from input to output, what will happen, this is 2 minus 1. So, sorry, 1 minus 2, this is minus 1, right. So, your so basically sorry, fan in minus fan out. Okay. So, what is happening here, so there are fan in is 2 and fan out is 1. So, if you move a resistor from input side to output, your number of resistor count will be reduced by 1, right. So, 2 minus 1 is 1. So, this will be given by the RV into number of fan in minus number of fan out. So, for a given node, how many fan ins are there and how many fan outs are there, their difference will give you the benefits. So, if the fan in is less and fan out is more, that means if you move a resistor from input to output, your actual number of resistors will increase, and if your number of fan out is less and fan out is more, fan in is more, then basically if you move a resistor from fan in side to fan out side, then number of resistors will be less. So, this fan in minus fan out will give you the benefits, okay, for each node, and this is a constant for each node, because we are not going to change any circuit structure, or for each node the number of fan in and fan out is same. So, this is nothing but a constant for a given node, right. So, the objective is here, depending on the n is fixed, AB is also fixed. So, I try to find out some RV such that this summation is minimum, right. So, I try to find out the value of RV such a way that this RV value is minimum for this summation. Okay. So, here the objective is that to minimize this value summation for each node RV value such that this will become minimum, where I have the feasibility constant, right. So, the number of edge weights should not less than this, right. So, this is the minimum formulation of the minimum area problem. So, if you want to minimize the resistors, we have this is the objective function and this is the constant. Okay. So, this way we can actually solve the minimum number of resistor problem as well. Okay. So, as a summary, we have discussed about the retiming, how it will improve the timing or the number of resistor of a circuit, and we have seen that this particular retiming can be mapped, can be formulated as a set of constant, feasibility constant and critical path problem, and then we can solve those inequalities using shortest path problem to solve this retiming problem. Okay. And also we can solve both for minimizing clock period as well as minimizing the number of resistor. And then one factor is important here is the delay value, that delay of those node, because this is not the actual circuit, because we are all doing in I mean it is a virtual kind of circuit, right, because it is in the physical chip. So, all the delay value, the performance of the retiming primarily depend on this delay value, how accurate is the delay, combinational delay estimation of those nodes, right. So, if we talk about any synthesis tool for any target architecture, they have a file, right. So, those file actually mention the delay of each node for the target architecture. So, now the retiming performance actually depends on the delay value. If your delay is not accurate, the retiming that will be done may not be as per the expectation. But if you have a really very accurate delay estimation for your all the gates of your design, then retiming actually works wonder, right. It will give you optimized circuit in terms of the number of resistors or clock period by automatically, right. So, the two factor, this is a polynomial time solvable problem, because all are kind of n cube algorithm shortest path problem. So, this is not a exponential or a NP complete problem, this is a polynomial time problem which can be solvable, but performance largely depends on that delay estimation of the nodes of your design. Okay, thank you.